guys, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this particular discussion, we're going to look at the concept of moments of inertia, and basically we're going to do an evaluation of this specific aspect of a triangle by finding its moment of inertia about the x-axis. So therefore, given this specific illustration, we have been given the base given as b, the height as h. There's a difference of course in height between that one. So we're going to have two similar triangles, whereby we're going to have these larger triangles formed by those specific apexes which I have indicating, and of course we're going to have a smaller one given as such. So we said from our last discussion that for us to find a moment of inertia about of an area of such a figures, we're going to choose a small element of course in that xy system to represent this specific total area. So in this case, we have decided that we can have that one which is going to be met by those specific dimensions of x and y. And therefore, for us, this specific area section is going to form part of this larger figure which we're going to consider for the moment of inertia. So in this case, then therefore, that a small element of area is going to be assisting us trying to define the moment of inertia. And for the x, the moment of inertia about the x-axis, which we are trying to find, we're going to consider this one from the general formula of the integral of the square of y given as such dA, where our dA in this case is going to be represented as the product of those specific measurements for dx and dy of the small area segment which we have chosen above. So in this case, we can have this moment of inertia represented as the product between the integral of the square of y. And in this case, for our triangle, we're going to consider this specific area being formed by a small section which I've chosen and shaded in this part. And it's going to be formed by a thickness of dy and the length of L given as such. So therefore, we are going to expect our formula to be given in this specific case, given as dy, which is the product of L dy given as such. So therefore, in this case, we have considered our area to be given as the product of L dy given as such. And therefore, this is going to be assisting us in trying to evaluate the total, of course, moment of inertia by evaluating the integral of that specific area. So we're going to express our L in terms of y. So we're going to express L in terms of y, and that is going to assist us in trying to represent this specific integral in of course an appropriate way. So for us to do that, we are going to consider the aspect of a similarity between the larger triangle and this smaller one which has been formed at the upper part with a base of L, and therefore we're going to consider there a specific length which is going to be the ratio between the length of L over B is equivalent to the ratio between the height of this small triangle over the height of the larger triangle, which is going to be given as h, the entire triangle, minus L, which is going to be the difference, is going to form the height of this small triangle, all over the entire height, which is going to be formed by h. So our L in this case is going to be represented by the product of b into h minus y all over h. And this is going to form our L in this specific representation for the formula for of course, moment of inertia represented as such. So in this case, we can do a substitution in our formula, and then we are going to express our moment of inertia about the x-axis given as the integral between the square of y, and then L is going to be substituted by b into h minus y all over h. And then we're going to have a dy given at this further end given as such. So in this particular case, then therefore we're going to do our integration evaluation in order to find this specific representation, whereby we're going to find this moment of inertia about the x-axis represented in the form of so I'm going to take this particular constant over b and h outside the integral sign, and we're going to do an evaluation from 0 to h of these specific elements we have found. And in this case, this is going to be given in terms of the square of y, which is going to be given as the square of y from this particular part. And then we shall have this particular element of h given in terms of h. So we're going to have our h given as such. So this is going to be the product. I've taken B and H out, so the product between this specific element of H and Y can be given in terms of y squared H, or rather I can just still give it in terms of H y squared, and then we're going to have that one minus, so the product of y squared and y negative y is going to give us the cube of y given as such, so y raised to power 3, and we're going to find the integral of this one with this respect to y given as such, and this is going to give us a product of this specific integral given as b over h as a common factor given as such, and then we shall have hy cube all over 3. So we have performed an integral with respect to y by raising this one to the power of 3 and then dividing by 3. And then the second aspect is going to give us y raised to the power of 4 over 4 given as such. And this is going to be performed over this specific stretch over from 0 to h. So in doing our substitution, the moment of inertia about the x-axis for this specific evaluation is going to give us the value of b over h. And then we shall have this one substituting for h, that is going to be giving us h times h to the power of 3, and that is going to give us h to the power of 4 divided by 3 minus h to the power of 4. So in this case, we are going to just do a direct substitution for this one. It's going to maintain its value. So we're going to have that specific formula. So if we do a simplification of this formula, this is going to give us a value of bh to the power of 3 over 3, bh to the power of 3 over 4. So we're going to simplify this formula by finding a common factor for the denominator, and this is going to reduce to a form of the value of bh to the power of 3 divided by 12, and this is going to form the moment of inertia about the x-axis for this specific section or the whole of this triangle, as we have just done this specific evaluation. So we're going to come across the different figures which we're going to use in order to evaluate the moment of inertia, and I'd like to request our members to kindly check our description boxes for various links of other similar videos. So that is it for now, guys. Bye, God bless you. Catch us in our next video.